I'm Bob Duhamel. Today I'm going to talk about data structures. I'm making this video because I got curious about the prospects of people who go to coding boot camps and found out that regardless of what their prospects are, what they were asked about in job interviews included data structures. And they didn't really learn much about data structures in the boot camps and had to go and learn about data structures. Well, I've been doing database management practically since database managers were invented, and I learned my own way of structuring the data, and I thought, well, perhaps I should learn something formal about data structures. So I did some Google searching, looked at some YouTube videos, and what I found were lots and lots of places talking about abstract theory of data structures, but I didn't find anything about how they're actually implemented or where they're used. And I also found that the data structures they were talking about had very little, if anything, to do with the data structuring I used in database management. But some of the structures I did recognize because I recognized them from other places. For example, in disk operating systems or in the operation of network devices. So I know a little bit about these data structures, but some of the other theories I was pretty much lost because I could not see how they were implemented or get examples of where they're implemented as much as I searched. And in fact, my experience is that if I'm reading something and I'm having trouble following it, that the person explaining it doesn't know what they're talking about. They're just regurgitating something they heard or read somewhere else. And these sites and videos pretty much had that feel. In fact, some of the videos were definitely talking heads just reading a script, and they knew nothing about data structures themselves. So I'm going to take my understanding of data analysis and data management and what I know about these data structures, and I'm going to make a couple of videos. This first one will talk about what I know about data structures and relate what you might read about them to some real-world examples, and then I'm going to find out about the other data structures I don't know about. I expect I may find that some of these data structures are merely data structure theory and something that's never been implemented. This wouldn't be unusual. For example, when I decided to write my own networking textbook, I decided to look into some of the things I saw in other networking textbooks and found out that they were simply regurgitating stuff that they read in press releases or other books. And a lot of the stuff that they talked about had never actually been implemented. For example, there's something you may read about in networking called 100VG any LAN. It's a type of networking that goes a whopping 100 megabits per second, which was probably pretty useful 20 years ago. And it's called any LAN because it could merge Ethernet and token ring networks into one happy network. So I did some research on that and found out that it was something proposed by Hewlett-Packard, but actually never made it anywhere in the marketplace. So you will not find 100 VG LAN anywhere, not even old installations. Another thing that's talked about in networking books is metropolitan area networks. Well, I looked into that and found out that that's something that never got implemented. In fact, the IEEE disbanded their Metropolitan Area Network Committee decades ago because it just turned out to be something that wasn't useful. So you find a lot of things in textbooks and websites and learning sites talking about things that may be highfalutin theory, but has no real practical application, and it's only being taught about because whoever's teaching heard about it or learned about it, and so they're simply regurgitating what they learned. Well, if you've seen my lectures and read my books, you know that's not the way I do things. I find out what's really going on. I find out what the practical applications are and how things are implemented. And so I'm going to tell you how some of these data structures are implemented and then learn some of the other ones I don't understand yet and explain them to you. So what are data structures and why do we need them? Well, you use data structures every day. Have you ever written a list? Have you ever read a book? Written an essay? These are all types of data structures. We just don't think of them that way because they're so familiar to us. So a list, just, shopping list, eggs, milk, cheese, whatever, that's a data structure. Another data structure is a book where we have a cover, we have a number of pages of data, and they're organized in chapters, and then we have a table of contents at the beginning that tells us where each chapter begins. And then we can read a chapter, we get to the end of the chapter, we get to the next chapter, we can plunge in by using the table of contents and start anywhere we want in the book. And that's a data structure. In fact, one of the data structures used in computers is very similar to a book. So why do we need data structures? Because of the way computers store data and because the data can be freely changed around. So let's take a look at how computers store data and then find out why we need data structures. So a computer stores data in what we call binary form. We have all sorts of mechanisms inside computers to store data. We have switches, we have RAM memory, which uses little tiny capacitors. You can think of a capacitor sort of like an air tank. You can either fill it up with stored electricity or empty it out. If it's full, it's one state. If it's empty, it's another state. We have sets of transistors where if one is on, it holds the other one off. If we turn that one on, it flips the other one off. And on hard disks or floppy disks, if you can remember those, we store data as magnetic spots that are either magnetized or not magnetized. We have CDs and DVDs where we have little pits in the plastic. So there's all sorts of ways to store the data, and we call this binary data because there's two possible states. And we refer to these states just for our own convenience as ones and zeros. So we will call one state a 1 and one state a 0. Typically, if a capacitor is full, it's a 1. If it's empty, it's a 0. If one transistor is on and the other one's off, it's a 1. If you flop them, it's a 0. But we refer to data as ones and zeros. When I talk about data being stored, I'll talk about ones and zeros being stored. Is it stored in memory? Is it stored on a disk? Is it stored on a CD? Doesn't really matter. We can just use the ones and zeros to tell us what's stored there regardless of the mechanism used to store it. Now let's take a look at how computers store memory and how we access it. I don't have to specifically tell you how one of these pieces of memory is stored, and by the way, I will refer to those as bits. So one storage mechanism that can either be on or off, full or empty, magnetized or not magnetized. We call one of those places a bit. And we organize them into groups, and eventually we settled on a name for a group called a byte, and that would be 8 of these bits together. The reason we did that is because it was convenient in early computers, just because of the size of them, to store them in groups of 8. So I'm going to show a memory block. So this is some memory. It could be RAM, could be ROM. It's storing these bits of information as one kind of entity. We don't need to know how it is, but we do need to know how to access it. There might be multiple chips in here, a whole memory subsystem that has memory refresh circuitry, and because certain types of memory will lose their information if we don't keep putting it back in, and chips to implement what we're going to do. But from the outside, we will see just a number of wires. I'm just going to draw a few. Draw that up there, and there's other wires in between. And in early computers, this would typically be 16 wires, and that would be called the address bus. And I'll explain what that means in a moment. And then on the inside, the memory was organized such that we could get 8 bits at a time. I already talked about that. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. And so these are the 8 bits we can get out at a time, and we call this set of wires the data bus, and there would be 8 wires on there. So with these 16 wires, we can put voltages on there or some other kinds of data. Usually it would be like 3 or 5 volts as a 1 and 0 volts as a 0, but it could be any kind of entity. But we put those voltages on there in a combination of ones and zeros, and we could have 16 zeros, 16 ones, or any combination in between. And by doing that, we could have 65,536 different locations that we call addresses. So think of it as like 65,536 shoe boxes, and each of those shoe boxes holds 1 byte of memory. You can think of it in other ways too, but I use the shoebox example. And these are numbered from 0 through 65,535. And the reason for that is that 0 is something we can specify on there, all off, all zeros. That would be the very first byte of memory. All ones, which would represent in decimal 65,535, would be the last byte, and any other combination of ones and zeros would be somewhere else. So essentially, we can put a address on here of any combination of ones and zeros. And so, for example, if we put all zeros here, the memory would crunch away and out would come the data on those 8 little bits of memory in that first address, that first set of transistors or whatever we are using to store that data. And if we put all zeros in a single one, then we would get the next memory location. So there's 65,536 times 8 little transistors or switches or some kind of entity in this little box that can store information, and we can pull out 8 of those at a time on our data bus up here. So that's how we look at memory. So basically it's just a list. I can think of this as a tall stack of shoe boxes. Here's shoebox number 0. Here's shoebox number 65,535, and all those other shoe boxes in between, each holding 8 bits of memory. So it's just a list, a long list, 65,536 items on this list, and I can randomly address any one of those here and get the data out there. So that's essentially how we see data stored. Now, if it's stored on a disk, each of these bytes would be in sequence, a byte here, byte there, byte there. So there'd be like 8 magnetic spots, 8 more magnetic spots, 8 more magnetic spots, one after the other. So they're just a string of bits on the disk. Or on a CD, it's a little string of pits, or whatever is being used to store that memory. But we can think of it like this. An address goes in, a byte of data comes out. Now, of course, with newer computers, this address bus has gotten much bigger, and the data bus has gotten much bigger, so we can address monstrous amounts of memory these days that we couldn't when I got started in this stuff back in the 70s. And we can pull out, today we pull out typically 64 bits at a time, but we still think of them 8 bits at a time. So we still address them 8 bits at a time. So our first address, although that may have 64 bits in the address, 64 zeros, that's the first byte. And then 63 zeros and a 1, that's the second byte. We may pull them out 8 bytes at a time, but we still look at it 1 byte at a time. And this memory can be used to store data. And another reason we still look at it 8 bytes at a time is because the most common way to use computer data is to store letters of the alphabet. And we have an interesting little code called ASCII. That stands for the American Standard Code for Information Interchange. This has been expanded into an international code called Unicode. I'll talk about ASCII first, and I'll give Unicode an honorable mention. But ASCII, we can store all of the letters of the Western alphabet, both upper and lowercase, plus numbers, plus punctuation, and have space left over for instruction codes to talk to printers or whatever, using 7 bits. Well, 7 is kind of an odd number. Early teletypes would use 7 bits to send their information. In fact, early ones used 5 bits, and then they could only do uppercase. Then we expanded to 7 bits with the ASCII code. We could do upper and lowercase. But because computers like nice even powers of 2, we go to 8 bits. And so if we take this combination of bits, 0, 1, 0, 0, 0, 0, 0, 1, we have agreed that this represents the capital letter A. And if we take 0, 1, 0, 0, 0, 0, 1, 0, we have agreed that that equals the capital letter B. And if we take 0, 1, 1, 0, 0, 0, 1, 0, notice the difference is there's a 1 here instead of a 0, that would be the lowercase b. And so we encode these letters of the alphabet in these 8 bits, and with room left over. And we have with this other bit here that we're not using, that gives us an entire other set of bits. With 7 bits, we can have 128 possibilities. With 8 bits, we have 256 possibilities. And no one's really figured out a standard for how to use those extra bits, but we can encode the alphabet in these 8 bits with plenty of room left over.